Okay, good evening. This is our lecture number 25th. So, in the previous lecture, we have discussed about the separated flow modeling. Okay, now we will discuss one more type of modeling approach, which is called as drift flux modeling. Okay, so in actual practice, if you see, drift flux is nothing but a subset of separated flow model only. Okay, because in case of drift flux model, what we see, we try to see that what is the relative motion between the two phases, and we take the advantage of that relative motion to define some of the very initial parameters. Okay, so whenever we will be using the drift flux modeling, this modeling approach will be helping us in defining some of the basic parameters based on the value of the drift flux. So ultimately, drift flux model is nothing but a separated flow model only, but here the specific focus is on the relative motion rather than the individual phases. Okay, so a true separated flow model is one in which we are solving separate continuity, momentum and energy equation for individual phases, and then we are considering the interaction between the two. So that is true separated flow model. But in case of drift flux model, once again we are interested in combined phase equations only. So my interest is in combined phase continuity, combined phase momentum and combined phase energy equation. But the only one additional equation I will be just considering for the relative motion between the phases, and by taking that help of that equation, we will be able to actually develop some of the basic criteria. So very detailed analysis we will not be getting from this, but some of the preliminary idea we will be getting. For example, if you have a vertical tube, so in a vertical tube, say if air and water are flowing in vertical direction, co-flowing together, okay, so then you can decide that whether the flow will be sustaining in that tube or it will be unstable and then it will be shifting from one condition to some other condition. Okay, so that type of initial idea actually you can get by just knowing the relative motion between the two phases. So for that purpose actually drift flux model is used. So its major applications are where relative motion can be easily determined, and this relative motion is not much dependent upon the individual flow rates of the fluids. Okay, so for example, if you simply consider a pool of water, so in a pool of water, if boiling phenomenon is happening, so what will be happening? There will be formation of number of bubbles, and these bubbles are actually rising in upward direction. Okay, so when the bubbles are rising in upward direction, in between the rising bubble and the liquid which is moving in downward direction to replenish the space vacated by the bubble, so that relative motion will be giving you some idea about the flow dynamics, some idea about the void fraction present in the system. In that type of scenarios we can use. Okay, so bulk, there is as such no bulk motion of the fluids. Okay, so that is what is given over here. So you can also see the relative motion for bubbly flow at low velocities in large pipes. So if you have large pipes and low velocity bubbles are actually having relative motion with the liquid, then majorly this relative velocity will be dependent on void fraction and it will be independent of the individual flow rates of the two fluids. Okay, so that's why under these scenarios we can actually apply the drift flux modeling technique. So typical applications of drift flux is in case of bubbly flow, slug flow and droplet flow. Okay, so all these are the cases whatever you are input giving for air at the inlet, it is not depending upon that. After that input of air, how now within the pipe these bubbles are actually oriented and how these are moving relative to the water, that is what based on which it will be giving you some idea of void fraction. Okay, whether rather than on the value of the input flow rate which is supplied at the inlet. Okay, so these scenarios will be occurring when void fraction is actually less within the system. So that is typically bubbly, slug and droplet flow. And if you consider other systems such as fluid particle systems, there also this will be applicable. So for example, if you have a slurry flow pipeline at low concentration, so there also the inlet flow rate of the particles will not be much involved. Rather, the relative motion between the particle and the fluid will be actually involved. So there actually you can predict the value of void fraction by just knowing the relative motion between the two. Is this point clear? So that's why in case of fluid particle systems, you can see different applications. For example, fluidized bed reactors. Okay, so in case of fluidized bed reactors, what happens? You have some particles which are oscillating within the fluid medium because of the relative motion. Okay, so there where settling of the particle will be happening, where particle will remain suspended with the relative motion. So there actually you can actually use the applications of drift flux. And it is many times also used to determine the rapid solution of unsteady flow problems, because if you have to do the actual analysis of unsteady flow problems, that will be quite complex. So if you are looking for very quick solution, then you can apply drift flux model. So let's first see what is the fundamental theory. So this equation number 1 and 2, these are something which we know from our very first lecture, from the second or third lecture when we discussed the nomenclature of the two-phase flow. So this J21 over here is something which is called as drift flux. Okay, so drift flux can be written in terms of V21, where V21 is relative velocity between the phases times alpha into 1 minus alpha. Okay, where alpha is nothing but volume fraction of phase 2, and typically if your phase 2 is a gas, then this alpha is typically called as void fraction. Okay, so majority of the time whenever you will be seeing this symbol alpha, it is majorly defined for fluid 2, and majorly it is termed as void fraction. Okay, then this second equation also we have seen that 1 minus alpha into J2 minus alpha into J1. Okay, now if you just do manipulation of this second equation, then from the second equation you can calculate the individual values of J1 and J2. So individual values of J1 and J2 will be 1 minus alpha into J minus J21 and alpha into J plus J21. Okay, so it means that if you simply use the homogeneous flow approach, means when relative motion between the phases is not there, then J21 will be 0. So for a homogeneous flow approach, simple values of J1 and J2 will be becoming 1 minus alpha into J and alpha into J. Okay. Now taking the help of these particularly this relation and these two relations, I can write value of alpha as, from the drift flux model, as J2 by J into 1 minus J21 by J. Okay, so one important point you have to remember over here, if I simply write J2 by J to calculate value of alpha, then this alpha is called alpha for homogeneous. Okay, because from this equation J2 by J will be true only if J21 is 0, and J21 represents the relative motion between the phases. So relative motion between the phases will be 0 for homogeneous flow. Okay, so typically you can say that your actual volume fraction for a relative motion fluid will be nothing but alpha of homogeneous times 1 minus J21 by J2, where this 1 minus J21 by J2 can be called as a correction factor because of the relative motion between the two fluids. Is this point clear? So this is nothing but acting as a correction factor. In a similar way, you will be able to recall that when we were defining the mean density for homogeneous flow approach. For homogeneous flow approach, we had just written mean density as alpha times rho 1 plus, 1 minus alpha times rho 1 plus alpha times rho 2. And this 1 minus alpha we were simply writing as J1 by J, and this alpha we were writing as J2 by J. So this is now nothing but density for homogeneous flow. If you consider the relative motion, then you will be having some additional correction factor. So this is correction factor in density. Is this point clear? So whatever the previous formulation we have discussed till now, based on the simple volumetric average or simple alpha, that is based on the assumption that relative motion between the fluids is actually 0. So if we consider relative motion between the fluids, then your definition of alpha will be this, and if you substitute this definition of alpha over here, then you will be having additional correction factor as rho 1 minus rho 2 into J21 by J. Is this point clear? Now we will try to see the applications of this drift flux approach, how this drift flux approach actually can help in determining different characteristics of the flow. Okay, and majorly you have to remember that this approach will be applicable where there is a strong relative motion between the phases, and this relative motion is not controlled by the inlet flow rates of the fluids. Okay, so there this approach is applicable. So one such example we can consider as gravity dominated flow regime with no wall shear stress. So you can consider, say you have a tube, and in that tube wall shear stress is say negligible. Okay, so wall shear stress is negligible, or tube is of actually very large diameter. So there also you can consider that at the core you are interested, and in the sides near the wall you are not much interested. Okay, so in this scenario, if you have say flow of gas and liquid, then what will be happening? So typically if you have gravity dominated flow with no wall shear stress, first is we are making assumption of steady flow. So in my momentum equations there will not be any time term. And second is if I consider a constant tube diameter and no acceleration of the flow is happening because of the change in area, in that case I will be having acceleration with the spatial parameter also equal to 0. Okay, so if both these things are 0, then for individual phases my left hand side of the momentum equation will be 0, and in the right hand side I will be getting pressure gradient term, gravity term including individual densities, and one interaction force. So F12 is force on phase 1 because of its relative motion with phase 2, and F21 here also this is F12 only but with minus sign, so it means this is force on phase 2 because of its relative motion with phase 1. Is this point clear? And of course you can see one more term that we typically use to write wall shear stress also, so that we are not writing because wall shear stress we are considering negligible. Okay, so typically if you consider, say you have a bubble column reactor, so in a bubble column reactor what you will be having? You will be having a large vessel. Okay, and in this large vessel, say from here you are adding some gas, so you will be having so many gas bubbles within this. Okay, so now these gas bubbles are not influenced by the walls of the container because container is of very large size. So here neither it is dependent upon the rate at which you are actually supplying the air into the tank. So it is majorly dependent upon their individual shape which is actually governing their motion. So in this scenario what you will be finding? Individual bubbles, because of their buoyancy force, they will be rising upward, and then the relative motion between the two will try to move them in the downward direction. So this is nothing but balance between the relative motion which will cause a drag force, interfacial drag force, and the gravity forces. Okay, so this type of situations actually we are now talking about. So in this scenario if you do this, say this is equation number 2, this is 1, so if you do 2 minus 1, so 2 minus 1 will give you that F12 is nothing but alpha times 1 minus alpha g into rho 1 minus rho 2. So it means for these type of flows, your interaction force is nothing but interaction force is majorly because of the balance of the interfacial and the weight and buoyancy forces. Okay. So it means that the relative motion is only dependent upon gravity term. Relative motion is not dependent on any other parameter. Okay. So wherever you are having this type of situation where majorly body forces are contributing the relative motion between the phases, there only you will be able to apply the drift flux model with good accuracy. Okay, if you apply it to some scenarios where other than body force is also responsible for causing the relative motion, there actually this will not be giving you the good results. Okay, so typically I can say that in this particular scenario, my body force is majorly responsible for the interaction force which is causing the relative motion. So it means relative motion is majorly dominated by the body force. Now if I have relative motion, so for this type of system I can simply say that relative motion will be function of alpha and properties of the system rho 1 and rho 2. Is this one clear? So majorly, now if I fix the properties, means if I consider say I have air water system. So for air water system now rho 1 and rho 2 are fixed. Okay, so this thing is also fixed. So I can simply say that relative motion which is indicated by drift flux J21, that is nothing but a sole function of alpha. Is this one clear? So relative motion will be becoming sole function of only alpha. So if in any system I know that how my drift flux is varying with alpha, then I can actually get some information about that system. Okay. So one typical plot is given over here. So here you have J21 in the y-axis along ordinate and alpha along abscissa. Okay, and in this is the point corresponding to alpha equal to 0 and this is the point corresponding to alpha equal to 1. So it means corresponding to alpha equal to 0 I have pure liquid and corresponding to alpha equal to 1 I have pure gas. Is this one clear? So in between this liquid and gas, I will be having a two-phase mixture where I will be having actually some value of alpha. Okay. Now, as I told you that J21 has become a single function of alpha only, so we have to determine that what functional relationship will be actually fitting this curve. Okay. So, for the time being, let us assume, we are not going into mathematical function, let us assume that this functional relationship is given by this particular curve. Okay, so this is the curve which is giving the relationship in between J21 and alpha. Okay, is this one clear? Now, this is coming from the governing equations. But I have one more equation which tells that J21 can also be written as 1 minus alpha into J2 minus alpha into J1. Where J2 and J1 are the fluxes, individual volumetric fluxes of the each phase. Okay. Now, when I will be substituting alpha equal to 0, say in first case I have a pipe and in this pipe I have co-current flow of two fluids. So first let's consider that air and water both are jointly flowing in this tube in the upward direction. Okay. So if air and water are co-flowing in upward direction, let's consider this upward direction, whatever volumetric flux I am having, that is considered as positive. Okay. So in upside, if both the fluids are flowing, then J1 and J2 I am designating as positive. Is this point clear? Both are positive. So in this case, when you will be substituting your alpha equal to 0, corresponding to alpha equal to 0, your value of J21 will be equal to J2. So when alpha is equal to 0, corresponding to this value of J21 is becoming J2. Okay. And when alpha is 1, then value is becoming minus J1. So here I am having value minus J1. Okay. And if you see the nature of this equation is nothing but a linear equation. So if I know the two endpoints, then I can simply join a straight line to show the nature of this equation. Okay. So now this straight line is a function of inflowing volumetric fluxes, and this particular curve is actually function of the nature of the system. Okay. The point at which these two lines are intersecting, that particular point is actually the operating point of the system. So it means that if you specify the co-flow of fluids in a particular tube with J1 and J2 volumetric fluxes, corresponding to that, within the tube, if your flow is in bubbly regime, then you will be having this much value of average void fraction within the tube. Okay. Is this point clear? All are clear with this idea? So I am having value of J1 and J2. Corresponding to that value of J1 and J2, if I am mentioning point if flow is bubbly, because drift flux will be applicable only when my relative motion is dominated by the body forces, and relative motion will be dominated by body forces when I will be having either bubbly flow, droplet flow, or if I have other type of flow, say annular flow or so, there relative motion is not dominated by the body forces. There other forces are actually interfacial forces are causing the relative motion. Okay. So that's why here here also interfacial forces are causing, but here interfacial forces are caused because of the gravity. Okay. But if you have say annular flow, then it may happen that if you have a very thin annular film of say 100 micron and adjacent to that you have gas, then in between these two what will be happening? In between these two you will be finding say your relative motion is because of the wall shear stress within the liquid film. Okay, so because of the wall shear stress also there can be relative motion. So because of this reason, what I am telling you that if my flow is bubbly for the given flow rates J1 and J2, then corresponding to that I can say that within the tube I will be having this much amount of void fraction. Okay. And this is for co-current flow. Now this co-current flow can be in upward direction and this can also be in downward direction. If co-current flow is there in downward direction, in that case what will be happening? I will be writing J1 and J2 as minus J1 minus J2. Okay, because say downward direction if I consider negative. So then corresponding to that also I will be actually getting some straight line only, and then I will be able to predict the flow parameters. Okay. Now if I have say second situation is counter current flow. Counter current flow will be existing for a system, say I have liquid, so liquid is flowing down and gas is moving up. So J2 will be positive and J1 will be negative. And counter current flow cannot exist for the reverse situation. Okay, I cannot have a counter current flow in which liquid is flowing above and gas is flowing down. So majorly counter current flow will be only sustaining if liquid is flowing down and gas is flowing up, because of the body forces. Of course, if you consider a tube and in that tube if you do a pump from the sides fluid is being pumped, and then from the top if you use a high flow rate blower or fan and that is flowing here, then you can have a counter current flow. But there your relative motion is not dominant because of the body forces. Their relative motion will be because of some other forces. So here we are considering where relative motion is because of the body forces. So when relative motion is because of the body forces, then our counter current flow will be only existing when liquid is moving down and gas is moving above. Is this point clear? So if I have this type of situation, then J1 will be negative and J2 will be positive. So when alpha is 0, J2 point is remaining there only, but when alpha is 1, in place of J1 now I will be getting minus J1 and that minus minus will become plus. So my point has shifted somewhere here. Okay, so in this scenario you can see for counter current flow my line is now intersecting with 2 points. So in this scenario, within the tube, all the time I will not be having the unique operating condition. My operating condition will keep on oscillating between these 2 points. So at some instant of time, if you just calculate the void fraction of the tube, you may find that value is alpha 1. At other instant, you may see the value is alpha 2. So you will not be getting a unique stable state. Okay, it will keep on oscillating between the 2 states. Is this point clear? So here what will happen? Some instabilities will grow and these will try to oscillate the operating point between the 2 limits. Is this point clear? Then I can have third situation in case of counter current flow, because if you consider co-current flow, in case of co-current flow, whatever value of J1 you choose, your line will be always like this. Okay, so if line is always like this, then always you will be having a unique operating point. So it means if you have gravity dominant co-current flow, always you will be having a unique operating point. But if you have a gravity dominant counter current flow, then for some reason, say particularly if lines are like this, then you will be having multiple operating points, and there can be some situation when your curve is becoming tangent to the system characteristics. Okay, your curve is becoming tangent to the system characteristics. So when it is just becoming tangent to the system characteristics, this particular point is called as situation of flooding. This is called as flooding point. Okay, flooding point means this counter current flow now will not exist. Okay, this will try to create some other issues within the system. And after this point if you go, then nowhere your characteristics are actually meeting, so then you will be getting no solution. It means you have some very chaotic or unstable situation. Is this point clear? So till now, yes please. Flooding point, in case of flooding point, if gas flow rate is high, then gas will try to carry the liquid. In place of liquid moving in downward direction, it will start moving in the upward direction with the gas. Okay, or if liquid flow is high, then some portion of gas, in place of moving in upward direction, it will move with the liquid in the downward direction. So flooding means instead of having the counter current approach, some portion of other fluid will actually start moving with the other one. So that is situation of flooding actually. So you want to go there, but something is pushing you back. Okay, so that is the limit of flooding. And even after that, no solution means very chaotic situation. When one is dominant, it will push it here, then other is dominant, it will move it above. So sometimes what happens, say you have this type of situation. Okay, counter current, liquid is moving down now, and gas is moving above. So when gas is dominant, gas will start moving the liquid up. When weight of liquid will start rising, it will form some sort of big liquid bridge over here. Okay, and when weight of the liquid bridge is growing, it will start moving down. So very chaotic situation will happen. Okay, you will not be able to define a very definite situation, And because of, in this scenario, when your liquid bridge is forming, then your void fraction will be changing. Liquid is more accumulating. When this liquid bridge is broken and moving with the gas, then void fraction is decreasing. So you will not be having a stable value of the void fraction there. Okay, and very chaotic situation you will be obtaining. So drift flux model you can see by just knowing the two equations. First is we should know the system characteristics, and second is this simple equation of straight line relationship between the individual volumetric fluxes. By just that you can actually predict that what kind of behavior your system will be having. Okay, so that is the idea of this. So very initial access if you want to make to the system characteristics, that you can do with the help of drift flux model. Okay, so now interesting point is we have come to know that what will happen, but interesting point is till now we were not able to determine the nature of these system characteristics. Okay, so how to determine the nature of this system characteristics, particularly this curve, that I will discuss in the subsequent slides. Okay, so basic idea of drift flux model is clear.
इसको
Yes.
फ्लडिंग और कोकरेंट फ्लो को मतलब डिफरेंशिएट कैसे करें, क्योंकि उस कैरेक्टरिस्टिक्स पे तो एक ही पॉइंट ऑफ उनका है.
No, not the same characteristic. In co-current flow, both the entire liquid and entire gas are moving in same direction. But in the limit of flooding, some portion of fluid can move co-flow and the remaining portion can continue moving in the counter flow. Understood?
इस इक्वेशन से कैसे पता मतलब करेंगे?
This equation will be only working if you have intersection within this. If you are going beyond this point, then whatever chaotic situation is existing, you cannot predict that based on this. Okay, you can simply tell only within this range. After this, this is no solution as per this. This is mathematically telling based on this model that there is no solution. But in reality, something will happen. So that whatever will be happening, that just now I have shown that what can happen. Okay, so in physical system, if you are flowing something, something will happen, but that will not be giving you the fixed value of void fraction, a particular type of flow regime. That will be giving you different type of chaotic situations. Okay. So this is one graph which shows that how system characteristics can be actually predicted. So these are the different experiments. So you can see different materials. These particles were tested in, these were the diameters of the tubes in which these experiments are done. And then you can see that this is, all these scatter points are nothing but experimental data. Okay. And in this experimental data you can see this J21 is non-dimensionalized with V infinity, where V infinity is nothing but the terminal velocity of each particle. It is terminal velocity of individual particles which are moving in the tube. Okay, and here you can see for different, so these all void fractions are experimentally measured. These are the experimentally measured void fractions. How to experimentally measure void fraction, that I will be discussing in the maybe next lecture. Okay, so here you can see that all this experimental data is actually clustering together, and this can be given with the help of this line. Okay, so here you can see this J21 by V infinity is equal to alpha into 1 minus alpha power n. So in the last slide I simply told you that J21 will be a function of alpha. Now what exact functional relationship is existing, that is something which people have determined from the experiments. And from these experiments you can see that J21 is becoming equal to V infinity times alpha into 1 minus alpha power n, and whenever we have fitted this data over here for this line, so this data is fitted for value of n equal to 3. Okay, and remember one important point, this data is plotted for value of alpha close to 0.62. After this is not plotted. What is the reason? Okay, so majorly if you see, These experiments are performed for solid particles. Okay, these experiments are performed for solid particles. Solid particles have rigid shape. Okay, so if solid particles have rigid shape, so what will be happening? Till their concentration is low within the system, up to that point only, their motion, their relative motion will be because of the gravity forces. Once their concentration is increasing, they will be forming large clusters, and once they are forming large clusters, then because of their weight, they will be settling down and they will not remain suspended within the fluid medium. Okay, so that is the reason that alpha close to 0.62 is considered as limit of drift flux model when actually it is applied for solid particles. But if you consider in place of solid particles, if you consider a fluid particle like bubbles and drops, so bubbles and drops, because of their deformable nature, these will not be these will be having high tendency not to interfere with each other and form separate big entities. Okay, so because of which, whenever we will be using this similar analysis for similar relationship for fluid particles, then it can be extended in the entire range of alpha from 0 to 1. Is this point clear? Okay, so how to get relation, that we have seen over here. Now comes that if we have to determine the flooding limit for a system, then how, by knowing the flooding limit actually, we can actually construct the system characteristics. Okay, so this is one, there are two methods, one is graphical method and other one is analytical. So analytical method I will not discuss, final equations are given over here, but graphical method, how we can do, if you do experiments corresponding to the flooding point, and if you report the values of J1 and J2, and all these values of J1 and J2, if you are recording corresponding to flooding point, okay, then what you can do, you can form a large number of straight lines. Now you can plot all these straight lines, and if you fit the tangent to all the straight lines, that will give you the system characteristic curve. Is this one clear? So a graphical method is, say if a question comes that some values of J1 and J2 are given, and it is given in the question that these values of J1 and J2 are corresponding to the flooding point. Okay, if these values are corresponding to the flooding point, then, and it is asked you to determine the system characteristics, then what you need to do, you need to first draw the multiple lines on actual paper, and then with scale, and then you can draw a curve with tangent, and ultimately what you can do, then you can write your equation as J21 equal to alpha into 1 minus alpha n, and then you can try fitting different values of n, which is actually fitting your this curve, which is tangent to all, and that will be giving you the behavior of the system characteristics for a particular system. Okay, so you can expect this type of question. Then we also have one relation that J2, if I just, in my previous equation, our equation of J21 is 1 minus alpha into J2 plus alpha into J1. Okay, from this equation, if I do little bit algebraic manipulations, I can also write J2 as alpha by 1 minus alpha into J1 plus 1 by 1 minus alpha into J21. And this J21 is ultimately a function of alpha only. J21 is ultimately a function of alpha only. So this entire quantity is nothing but some function of alpha, and this, then I can say that J2, J1 is nothing but having a linear relationship. Okay, so if my J2 is y, J1 is x, then this alpha by 1 minus alpha will become my slope m, and this entire quantity will become intercept. Okay, is this one clear? So I can say that relationship between J2 and J1 is actually linear. So whatever I am plotting over here, same thing I can also plot on J2 versus J1 curve. Okay, and on the J2 versus J1 curve, all these lines will be linear, and these individual lines will be corresponding to different values of alpha. Okay, so if you see on J2 versus J1 plot, then you can see this is J2, this is J1, and these are the different straight lines corresponding to different values of alpha. In first quadrant, my both J1 and J2 are positive, so flow will be co-current. In second quadrant, in third quadrant, both J2 and J1 are negative. Here flow will be again co-current but in downward direction. So this is co-current upflow, this is co-current downflow. If I have J1 is positive and J2 is down, it means liquid above and gas down under gravity dominant conditions, that will not be existing. So here operation is impossible. Okay, in the fourth quadrant operation is impossible. And in this regime where I have a counter current flow, means liquid is moving down and gas is moving above. In this case, I will be having limited region of operation, because here I will be having the existence of flooding limit. So whatever this particular system characteristics I am having over here, this system characteristic if I draw, that will be mostly covering my second and third quadrant, and here this is the flooding line, and above this I will not be having the existence of the solution. Okay, is this point clear? So this is whatever this theoretical thing we have seen, this is also shown for different experimental data. So experimental data is actually within the flooding limit, experimental data is obtained, and it is shown that these experimental lines corresponding to the given values of void fraction are almost following the straight line. Okay. Okay, now this is something which is correction to the theory. Let's not discuss this. Let's simply go to the problem. Okay. So what we have a problem where water is flowing through a vertical duct at 70 degrees Celsius and 35 bar pressure. The drift flux is given as function of void fraction J GF. So G is gas, F is liquid, equal to 0.8 into alpha into 1 minus alpha square in meters per second. So this equation is given, it means system characteristics is already given. Okay. What we need to do, we need to determine the void fraction for the following values of JF and JG. So what we need to do?
J2 is equal to something into J1 plus J21 over function. Line is more I compare.
Tell me what I can do. This one? Okay, so what I need to do? J2 equal to alpha by 1 minus alpha into J1 plus 1 minus alpha into this. So from here I will be able to calculate value of what I will be able to calculate from here? Function of J21 in yes. So there are two things. One is J2 and J1 are given to you. You can simply use here the equation of J21 and then you can actually solve this equation. Okay, so for each case you have to solve this equation. So this will be a complicated equation once you solve it.
Graph पर बनाने के लिए।
So other solution is, what you can do, you can plot this equation in terms of graph, drift flux versus void fraction, and then what you can do, for alpha equal to 0 and alpha equal to 1, you know the values of J1 and J2, you can obtain, and you will be finding different straight lines, and corresponding to each value of the JF and JG, you are now getting a different values of alpha. So say alpha, all these are nothing but alpha values for each case. So please do it and then try to find out these values. This is easy. Either you can make this graph. On this graph now you need to draw multiple straight lines for each case. And wherever your straight line is intersecting, corresponding to that whatever point is there, that is actually the value of alpha. This is graphical approach, and analytical approach is in the previous equation. You simply replace J21 with this equation, 0.8 into alpha into 1 minus alpha square. Okay. If you replace with that, then also you will be able to get the. Now if I
हमें पता कैसे चलेगा पीक कहाँ पे आएगी और पीक कहाँ पे आएगी और
simply you have, what is the range possible for alpha? 0 to 1. In the range of alpha from 0 to 1, substitute different value of alpha and draw. That is also, there also you will be finding a complicated equation will become. Okay, now if I reverse the question, let me reverse the question. If I tell you that this flow is happening and all these data is corresponding to the flooding point, now you need to determine the relation, say JGF equal to some constant C times alpha into 1 minus alpha n. You need to determine this relation. Can you do it? How can you approach now? So again the same question. Now all these data are corresponding to flooding point, okay, flooding limit, and you need to now find the value of C and N. How can you do this?
उसी में पुट कर दो उसी में पुट करेंगे उसी इक्वेशन
Okay, there we will be putting then
वहाँ से सी और एन के बीच में रिलेशन
that equation is not applicable only for flooding point, that is applicable for entire range.
फ्लडिंग पॉइंट के लिए भी
Okay, if you substitute, let me show you. So here now you will be substituting J21 in place of this C. This will be becoming a relation of C and N. Now how you can calculate? You don't know alpha, you don't know C, you don't know N.
तो वो टेंजेंट ड्रॉ करके
One is by drawing tangents, and any other approach? Any other approach? While I was explaining you the graphical approach, I told you that there is one more approach which is analytical approach, but I just forgot to tell them. So as per the analytical approach, if you calculate the slope of this and that slope, if you equate with slope of this equation, okay, so you have this J21 equal to 1 minus alpha into J2 plus alpha into J, all these straight lines, these are following this equation, and this J21 equal to C times alpha into 1 minus alpha n. This curve is this equation. If you take the slope of both these and if you equate the slope of both these, that will be your point of intersection. Okay, so if you do this mathematical analysis, you will be finding that J2 can be written as alpha square into V infinity n times 1 minus alpha into n minus 1. Okay, and Basically what you have done over here, you have written J21 by V infinity as alpha into 1 minus alpha n. So consider V infinity as nothing but equal to C. Okay. So if you calculate the slope of these two lines and then if you equate these two slopes, you will be able to get the value of J2 and J1 as using these two relations. Fine. So these two relations are nothing but, these are volumetric fluxes corresponding to the flooding limit. Is this point clear? So these two are nothing but the volumetric fluxes corresponding to the flooding limit. Now, if you have data of J1 and J2 for the flooding point, then using this data of J1 and J2, you can substitute in these equations. You will be getting a system of equations and then you have to solve that system of equations for values of V infinity and n. Is this point clear? Yes, V infinity, n and alpha.
सर अल्फा तो स्लोप से निकल गया ना.
What you do, all these values whatever I have given, consider that these are the values corresponding to the flooding point. Okay, and corresponding to these values you try to solve this using this approach and then tell me in the next class that have you got the answer or not. Okay, is this point clear? So I will be posting this lecture. So in this lecture whatever the data of JF and JG I have given, consider that these values of JF and JG are corresponding to flooding point. Okay, and then take the help of these equations J2 and J1 along with this equation. Of course this is applicable everywhere, and then you try to find out, then you try to give me the outcome that what will be value of C and N when we are actually calculating the, when we are deriving the master curve from the data of flooding point. Okay, all are clear with this idea? So all of you, problem is clear to you? So if problem is clear, please do it and let me know solution in the next class. Okay, okay, then we are stopping at this point.